Okay, we're going to look at number 4 from the 2003 AP Calculus exam. This was a common question on AB and BC. I have not read the question. I've only glanced at it enough to know that it was a common question. And so you're going to get to see me process and read the problem for the very first time. And let's go ahead. And I see a graph of f prime. It looks like it has 2 lines and a semicircle. And yes, it does. It says f is defined on -2 to 8. They give me an initial condition, f of 1. F of 2 is 1. We're given the graph of the derivative, so I'm ready for the net change there. I'm probably going to have to do 1 plus some integral from 2 to x of whatever. Anyway, so I'm just thinking that. Number A, does the graph of f have a relative minima, maxima, or neither at x equals 6? And give a reason for your answer. I'm going to type this solution. There's really no arithmetic or what students consider general math to be done. And so I'm looking at the graph of f prime. I can see that 6 is a critical number. So f prime of 6 is 0. However, f prime of x does not change signs at x equals 6. Therefore, the graph of f has neither a max nor a min at x equals 6. There we go. We don't have to do any real work explaining how we know f prime does not change signs because we're given the graph of f prime. If you want to kill it dead, and I get to do this easily because I'm typing, f prime is positive. I'm not even going to do that. For the sake of time, I'm not going to do that. I may end up biting myself or kicking myself when I see the scoring solutions later. All right, so the derivative does not change signs. Therefore, there is no max or min, and they gave me the derivative, so I don't have to go through any real calculus or arithmetic to show how I know that. I feel pretty good about that. Let's look on to B. On what open intervals is the graph of f concave down? Now, when I see concave down, I immediately want to think my second derivative is negative, which is true. However, you always want to explain or give reasons tied to specifically what they give you. They gave me the graph of f prime, so I would rather think of concavity as it relates to f prime. Well, if f prime is negative, that happens when if f double prime is negative, that means f prime is decreasing. So there's my game plan. And so I'm going to, again, type my solution just for the sake of time. And I can say that f is concave down when f double prime is negative, which occurs when f prime is decreasing. And then I'm going to say f prime is decreasing on the intervals -2 to 0, u, lazy u, 4 to 6. Therefore, the graph of f is concave down on, and I get to copy and paste. Yee-hee! Too bad we can't do that on the actual AP exam. On the intervals that. There we go. I left out the R in the word interval there. So f is concave down, and f double prime is negative. Prime is decreasing. Okay, good. Find the value of this limit or show that it does not exist. The instant I see a limit, I will assume it is an indeterminate form. And so, all right, I'm just deciding what I want to do here. So we're looking at 2. Okay, so I'm going to do this. If you want to establish indeterminate form, you want to look at numerator and denominator separately. So the numerator is 6f of x minus 3x, which is going to be 6 times f of 2 minus 3 times 2. And I'm looking here, f of 2 is 1. So they gave me that information. So that's going to be 6 times 1 minus 6. That is 0. So the fact my numerator is 0, I really feel good about the limit being an indeterminate form. And there's one thing about this numerator limit that I want to establish before I move on, and that is that in order to evaluate the limit of f of x as x approaches 2, I just plugged in 2 for f of x, which is safe. You can do that in this case, but only because f is a continuous function. You cannot assume that the limit as x approaches 2 of f is equal to f of 2. You have to know that f is continuous. So to be safe with that step, I'm going to say that the limit as x approaches 2 of f of x is equal to f of 2 because f is continuous at x equals 2. And as I'm writing that, I was thinking, I know f is continuous because I can see the graph, but I don't. I see the graph of f prime. So now how do I know that f is continuous? Well, f is continuous at x equals 2. Holy cow, this is getting long. This is me covering my rear end. F is continuous at x equals 2 because f prime is continuous at x equals 2. So that kind of goes back to the f is differentiable, therefore continuous. I'm looking at a continuous derivative from -2 to 8. Therefore, I know that f is continuous on that interval, which allows me to say that the limit as x approaches 2 of f of x is equal to f of 2. Wow, that was a lot of garbage talk. It's not garbage. It's good, sound mathematics, but it's a lot of writing, isn't it? I don't know. All right, so now the denominator limit as x approaches 2 of x squared minus 5x plus 6. That is a polynomial that is continuous, so that'll be what, 4 minus 10 plus 6. That is also equal to 0. Therefore, by L'Hopital's rule, I can say that the limit as x approaches 2 of my original fraction, or I should say my original function, is going to equal the limit as x approaches 2 of the derivatives of the numerator and denominator, which will be 6 f prime of x minus 3 over 2x minus 5, which would be 6 f prime of 2 minus 3 over 2 times 2 minus 5. That ends up equaling f prime of 2 is 0 minus 3 over 4 minus 5. And that is the step where you can stop. That would equal 3, but I'm going to cross that out just in case I made some ridiculous mind-numbing error. And then number D, that C ended up being a lot longer than I thought it would. Number D, find the absolute minimum on a closed interval. All right, so this is an extreme value theorem question. Absolute minimum on a closed interval. We want to consider my endpoints, and we are on the interval -2 to 8. I want to consider my critical numbers, which are when f prime of x is equal to 0, which occurs at x equals -1, +2, and +6. You very well may get a point simply for listing all of the candidates. Now let's think about what we're looking for. We're looking for an absolute minimum. So the absolute minimum can really only occur at the endpoints or at a local minimum. So I'm going to look very closely at my critical numbers. And we have already established in part A that 6 is neither a max nor a min. So I can discard 6 because of part A. So I'm gonna discard 6. And I'm just going to say C, a little hiccup, C part A, part A. And then if you look at the other critical numbers, you have x equals -1 and x equals 2. And I notice that at x equals -1, my derivative changes from positive to negative. That would be a local maximum. So I'm going to discard x equals -1. So f has a local max, and I have to explain why I'm no longer going to include it in my analysis later on. F has a local max at x equals -1 because f prime changes. And I like the word changes. Some of my students like to say the word goes. F prime goes from positive to negative. That just sounds informal and lazy. I don't know. F prime changes from positive to negative at x equals -1. So now I really only have three candidates to consider. I have x equals -2, x equals 8, and x equals 2. And I need to now evaluate my function at each of those candidates. I need f of -2, I need f of +2, and I need f of 8. And I believe this is going to take a little bit of time. And this goes back to what I was very quickly referencing in my mind earlier as I was reading the given information. We have, okay, this is kind of nice. We have an initial condition. We know that f of 2 is 1. So I can actually come back down here. I know f of 2 is 1. I need f of -2 and f of 8. They gave me the derivative and they gave me an initial condition. So f of -2 is going to be f of 2. I have that value. There's my starting point. Same thing down here at 8. I may do f of 8 first. I'm going to start at f of 2. And I need to know, how much do we change from x equals 2 to x equals 8? How much do we increase? How much do we decrease? And the amount of increase or decrease is found by measuring your antiderivative of the integral. We're looking at the derivative. We're looking at f prime. My wording is all messed up. So I'm doing the area under the derivative. And if I measure the area from 2 to 8, that tells you the net change on that interval. And the integral from 2 to 8 of f prime, because I have the graph of f prime, is going to be found through areas. I know f of 1 is 8. I'm sorry, f of 2 is 1. And then for the definite integral, I'm going from 2 to 8. And this is an interesting one. So I'm looking at 2 to 4. 2 to 4 is a triangle with base 2 and height 2, and I can see that that is an area of 2. For the rest of it, I'm going to do that big rectangle. So if you go from 4 to 8, you can see a rectangle that has an area of 8, and I want to subtract the area of the semicircle, and that will leave me the pieces that are below the semicircle and the x-axis. So that's going to be 8 minus the area of that semicircle would be half pi r squared. I'm looking at that very quickly. And the 8 minus half pi r squared is the area from 4 to 8. I'm going to leave it like that for now. I'm going to come back to it in a second. I now need to do the area or find f of 2 or f of -2. So that's going to be f of 2 plus the integral from 2 to -2. And it is okay to go from right to left. You just have to be mindful that that is a negative direction and impacts the sign of the antiderivative's value. So f of 2 was 1 plus, and now for that area, this one's going to be a lot more convenient. Oh, this is really nice. So I'm looking, okay, so from -2 to 0, I see a triangle with area 2. That is below the x-axis, but we're going from right to left. So that will be an area of +2. That's from -2 to 0. And then I'm looking from 0 to -2, and I have two congruent triangles, one being above the x-axis and one being below. So they will negate each other. Those will not do anything. So we're done. So I may just say +0 for the rest of it, I guess. And that's really easy to see that that is 3. I'm looking for the absolute minimum. 3 is larger than 1. Now what I have to do here is figure out what is going on with 2 plus 8 minus half of pi r squared. I do need to clean that up. So that's 1 plus 6 minus 2 pi. And all I have to do is enough work to determine whether that value is less than or greater than 1. I can already throw 3 out. 3 is not my absolute minimum. We're looking for the value. Yes, we're looking for the actual value, not the x-coordinate. And 6 minus 2 pi is going to be a negative number. So 1 plus that negative will be less than 1. Therefore, I can now see the absolute minimum is going to be that value at f of 8. So the absolute minimum is 1 minus 6 minus 2 pi, and I'm going to leave it like that. It does say justify your answers. In the case of an extreme value theorem, your justification is all the work. Where you found your critical numbers, you considered endpoints, you found the values of the function, and so I don't have to do any more work. And that was a cumbersome problem towards the end. A and B, pretty nice. C and D came in a little bit more worky. Now, they are fairly traditional questions. They just require a lot of work.